Okay, so it's time, and I'll start. So last time I left off at just the spatial interpolation of with the inverse distance, and Kriging, and I said we'll do the model fitting and calibration, validation, all those things in this session, along with the content from this session. So this week 12 session was almost entirely fitting the model and checking the accuracy of the model on the validation data set. So we'll quickly go through all the codes. One question I want to ask. So since one person is here, I'll ask you that were you guys able to access the codes that were shown in the class by sir? You can type yes or no, because I have tried and I have not been able to download or even see any of the codes that were shown in the sessions. Okay, so I'll take it as a no. So because of that problem that we are not able to access the content that is being shown in the session, the codes, the scripts, and the file, we will not be able to discuss the last problem, that is the complete model, where we not the complete, the combined model, where we combine different models in the last video of this entire machine learning in soil and crop management. So sir shared one file which was two-step .zip. So I'm not able to find that file. I'm not able to download that. So I will not be able to discuss the things related to that. But we will discuss all the linear regression and then the other type of continuous regression and categorical models. We'll discuss till then. Okay, so let me start. So first we are going to discuss uh, linear regression with single variable. So one independent variable and one dependent variable. So we'll load our i3 library, and we'll load the library mass for the data and the functions. Then we'll load the USYD soil1 data, and we'll store that data frame into the variable soil.data. So you don't need to put data, as I have mentioned many times in the last session, that this dot and all is not required, but just to remain consistent, I am using the same notations that are being shown in the session. And this is the line where you fit the model. So this is a linear regression model where when we say CEC and then similarity sign with clay, we are saying that CEC is something we want to predict, and clay is the independent variable which we want to use to predict it. And also this one, if you are not familiar with, so here we are just omitting everything and keeping only the clay and the CEC column from this soil data table. So we'll do that. We'll omit all the other things. So if you go and see that mod data, you'll have only clay, that is the independent variable, and CEC, that is the dependent variable. And here we fit the linear regression model, which says that our target variable is CEC and our independent variable is clay. And these are all available in a data, that is the model.data, mod.data. And you can check what is the line that this model has used to fit. So there is an intercept and there is a slope for the clay. Okay. Now we have seen there are a lot of parameters which can be used to check the goodness of fit of our model. So there is also a function goof which we will use to check check the alignment or the replicability, or we can say the goodness of our model. So later on we'll use for categorical model there is a different goof, that's a goof cat. For regression model we'll use the goodness of it, that is goof function directly. And it is said that if you don't give the type, basically this type is going to decide how many goodness of fit parameters you want. So if you have given type DSM, it will give some parameters. If you give type specs, it will give some more parameters. So if you give DSM, digital soil mapping, it is going to give R square concordance, the equation of which is shown in the PPT, and then mean square error, RMSE, and bias. And if you give spec along with these things, it is going to give you some more RPD IQ. Okay, so this is what we have, fit the model. Now let's see about the calibration and validation with the subset. So previously, what we did here when we fit the model, we gave all the values of the CEC and all the values of the clay column from the data set, right? And then we got the goodness of it. But usually, when we are making a model, fitting a model, we will try to uh, divide the data set available to us into some calibration data and validation data. So from this 146 values that we have, we will divide it into calibration and validation. So let's do that. So here we are going to use 70% of the data for our calibration purpose. So, so training is just going to be randomly selecting 70% of the data from our mod.data. And so these are the indices that are being selected. So these the points, the values at these indices will be used for the calibration purpose. Now, now again we are using the linear regression model to fit the thing. Now, if you see carefully here, we are using data which is not the entire data right now. It is just the training data. So we have fit the model now, and now using the fitted model, we can try to get the goodness of fit of for the calibration for the like the calibration data set, training data set. So here you see even the training data set doesn't have very good R square, but let's see how the validation data set performs. So when we are selecting only the training data, we use the our data frame and then square bracket training and then comma nothing. Comma nothing means that you are selecting all the columns. But when we want to avoid these, now we have used up these data for calibration purpose. So for validation purpose, we don't want this training data. So you can just put minus of the training data, and this is going to give you those indices which are uh, means not, this is going to use subtract these indices from the model data and use this for validation. So you see when we did minus training set the minus training, we will get something like this. So minus 14s, whenever there is an index with minus, so the R is going to ignore that index in this index. So that's how we separate the calibration and validation. So now we have fit the, predicted the values for our validation data, and we again try to get the goodness of it. So if you see here, for some reason, the model that we have trained, this model has an R square value of 0.54, which is a little better than the calibration data set. And that can happen based on what kind of data you are having. Now, this was single variable with all the data set means with the training data, all the training data training used to train the model at once. Now let's do the leave one out cross validation. So what leave one out cross validation will do is that it will predict the value at one point, as you can see this point, by fitting the model for the rest of the points, and it is going to do that for all the points. So we need a for loop for that. So what we do is we just initialize one variable that is going to be a numerical variable, and it is going to be zeros with the size of number of data that we have in our mod data. So if you see here on the right hand side, the LWO pred is 146 with all the values as 0, and these values are going to be filled in this for loop, which is going to run 146 times. So the line number 37 is telling us that we are fitting the model with data except that particular index where the for loop is running. For loop is running, and then we predict the value for that index using the model that we have trained. So pretty straightforward, and let's see what is the goodness of fit for this. So we get a goodness of fit of 0.4066. So if we see the two plots, if we compare the two plots, so why we are seeing less number of points here is because this is plotting only the validation data set, whereas in case of the leave one out cross validation, it is using all the 146 points, and it is giving us a trend line. Okay, so that's it about the single variable linear regression, and let's go to the multivariate linear regression. So again, we are going to load all the packages. Let me clear everything up. Again, we are going to load all the packages, i3, raster, rgdal. Then we are going to load our data set, that is the edge-Royce spline carbon. And we are going to change the name of the east and north to x and y using this line. And now what we want to do is we see these values. Let's look at these values. We want to predict the organic carbon or the carbon content in the soil from the depth 0 to 5 centimeters, right? So these values we can either predict the values as it is, or we can take some kind of data transformation and predict them. And we saw from previous session, or I guess previous session, that doing the log transform makes this data more normally distributed, right? So we are going to do the normal distribution. So we are going to take the natural log of this, and that will give, and we'll store that in a log of C stock between 0 to 5 centimeters. Now we are going to get more covariates for this edge Roy covariate data, and we are going to tell the R that the x and y in this spline edge Roy spline carbon, they are actually coordinates. So we'll use this line to convert this edge Roy underscore spline carbon from a data frame into a spatial coordinate system. And yeah, so we'll do that. Now we are going to stack the other covariates, that is the elevation TWI, RADK, Landsat B3, Landsat B4, that we got from the edgeroy covariates. We are going to stack them, and we are going to use this stacked data set to extract the information at these edgeroy spline points using a simple method. So when you say simple method, we mean that we are going to do the nearest neighbor interpolation. So if you look at the interpolation, there will be linear interpolation, then nearest neighbor, and then spline. So when we say simple here, we are saying that we are using the nearest neighbor interpolation technique. So what this extract co-stack edge-roy spline means is that you have some data at this co-stack, which is your data that you are going to use to get the data at this edge-Roy spline carbon x and y locations. So this is your, you can say this is your training, and this is your new data, if you want to say it like that. Otherwise, you can just say these are the data that are available, and we are going to we are going to interpolate or extract the data at these points. So that's only the significance of core stack here. So let's do that, and then store them into DMS underscore data. So if you look at the DMS underscore data, it is going to be in spatial format because this Cove stack and edgeroy underscore spline carbon both are in spatial format. So we need to convert it into the normal data frame. So we'll do that and we can have a look at the data frame. So these XY are the locations in the edgeroy spline carbon, and we got these elevation TWI, RADK, Landsat B3, Landsat B4 values by using the Cove stack and the edgeroy covariate data. Okay, so now you can also see the structure. So previously, if it was in the form of a spatial coordinate system, now it is in table with all the values being numerical or integer. Okay, now see, we want to fit the data. We want to fit a multi variable linear regression. So we don't want most of the values. We only want 2, 3, that is the x and y, and 11 to 16, that is the elevation, TWI, RADK, and Landsat V3, Landsat V4. So we are going to remove all the other values from our DSM underscore data, and let's see what we get. So when we removed it, we have removed all the x 0 to 5, 5 to 15, 15 to 30, all the unnecessary data, and we are going to fit the model for this particular data. So now we want to fit, so we have to choose which value is going to be our dependent variable and which values are going to be our independent variable. So if you look at, before we are doing that, we are doing something more, that is removing the NaN values, because they can be problematic when we are fitting the model. So if you look at the data, if there is no NaN value, that is very good. But when we have a large sum of data, most of the time we cannot check, keep on scrolling down and checking the values, right? So for that we use these two scripts. That is, this one is going to tell us whether there is any NaN data. If you give integer 0, NaN or missing data. If the output is integer 0, that means that there is no missing data. But still, for security, we are going to keep only the data that is complete. So we do that by executing this line, and now we are fitting our model. So again, here what we are doing is we are fitting the whole data, because we have not used any training here. So we are fitting the whole data as of now. So we have our dependent variable as the log of the carbon available in 0 to 5 centimeter depth, and the independent variables are elevation, TWI, RADK, Landsat B3 and B4. So we fit the model and we can get the summary. So we can easily see the slope. We should be able to see the F1 score, yes, and you should be able to see the standard error t value for the model that we have fit, the minimum and the maximum with the mean and median and the quartile ranges. Now let's try to again okay, so we are going to see, when we have fit these models here, there may be some parameters or some of the features among these 5 features that are not really related to the uh, log C stock 0 underscore 5. So this approach or this line is used to this code, that is the step code, is used to identify which variable are the most important in this linear regression, and ignore all the rest. So when we run that and we check the summary, that then you will see the elevation and Landsat B3, only these two are very strongly related to our log C stock underscore 5, that is the dependent variable. So we can ignore the other 3 variables and make our model more simpler. And that's what we are going to do for the calibration and validation. So we set the random seeding at 1 to 3. Then we divide our data set into 70% for training and 30% for the validation. So we split the data. Now we fit the model for the training data that we have separated, and now we can check the uh, goodness of it for our calibration data. So first we make the predictions for our calibration data, and then we get the goodness of it. So if you see, the R square again is 0.26024006, which is not very good. And when we go to the the validation data set that is accessed using the minus training index, first we do the prediction and then we check the goodness of it. So it is even worse when it comes to the goodness of it for the validation data set. So we can obviously play around with variables, include the other three variables also, because if you see here, we have only used the elevation and Landsat B3, because the other variables are not showing much correlation with the log C stock, that is the dependent variable. So you can try to include the other variables and see if it is going to increase the R square value. So you can play around with that. Okay. Now let's try to see this the predicted values on our data frame, on our map. So basically, to plot it on a map, as we discussed earlier, what we have to do is first get the indices of the points where the data is available. So if you can go ahead and look at this statement in the last video, what I will just briefly explain, that what we are doing is we are trying to identify the indices where the data is available, and from that index, what we are doing is we are checking what is the minimum x and maximum x, and making the grid using this line, and then we are combining them into a temporary data frame. So if you look at this temporary data frame, you will see that this data is in the form of a grid. This x and y is in the form of a grid, and we have the values of the elevation, TWI, RAT-K, and the other independent variables at these points inside the grid, and we are going to use them to predict the value of the carbon stock in the 0 to 5 centimeter using our linear regression model that we have trained. So you can see the structure of the data. You see x and y are in numericals, and you have the elevation, then TWI, and other independent variables. Now we perform the prediction. So we use this data that is stored in the temporary data frame, and we use save the predicted carbon content in the variable map.mlr, multiple linear regression, and then sorry, we have to redo this, and then we can bind the data, that is the temporary data, the x and y of the temporary data, and the carbon stock log of the carbon stock that we have predicted into this MLR. And then if you see, map.mlr will have x and y and the corresponding concentration or the carbon content, log of the carbon content in the 0 to 5 centimeter depth. Now, when we have this, now we can use this to plot our map. So if you see, we are making a raster from XYZ, where X and Y are the coordinate system and Z is nothing but the log of the carbon content. So we make the raster here and then we plot the raster. So the Z here is showing the log of the carbon content from 0 to uh, 5 centimeters. So that's about multiple linear regression. Now let's move on to some more interesting linear regressions, sorry, the regression algorithms. So we will see here decision tree, and then after that we are going to see um, cubist, then we will see random forest, and for the last in the regression we are going to see universal kriging, and we'll briefly talk about how this universal kriging is different from the ordinary kriging. Actually, also I would like to discuss very briefly and conceptually what and how we obtain the parameters, the weights in the kriging method. So in the last session, one of the participants had the problem, but since I was unaware, and it was a little out of the scope of this syllabus also. I didn't discuss that, but I have today we'll try to see if I can explain to you the basics of how this kriging weights are obtained. So first we'll see the regression tree. So we'll again load the data set ith, right? And then you need the regression for making this regression tree. You need the rpart library package, so you can download it. I have it already downloaded. And these I don't want to repeat this, but this is basically the same thing. We are importing the points, and then we are renaming them, the easting and northing to x and y. Then we are taking the log of the carbon concentration or the quantity between 0 to 5 centimeter. Then we are loading the edgeroy covariates, which are the elevation, TWI, rad K, Landsat B3 and B4, and we are assigning them to the coordinates. And we are assigning our edgeroy spline carbon to also the spatial coordinate system so that we can extract them. Then we are tracking all our raster covariates, that is elevation, TWI, and the other independent variables into a cove stack, which is a multi-layer raster file. Then we are using this multi-layer raster file, that is the cove stack, to get the value or to extract the value of these independent variables at the locations that are available in the edgeroy spline carbon using the simple method, that is the nearest neighbor interpolation. And then we are storing it into a data frame, which will again be a spatial coordinate system, since this cove stack and edgeroy spline carbon are in spatial coordinate system. So then we convert it into a normal data frame, and then we visualize it. And here we are just removing all the unnecessary variables, and we are just keeping the independent variables that we want, the log of the concentration of carbon that we want, and the xy location. So I am just going to execute all these lines at once, and we'll see the DSM data. That is the, so we have finished the pre-processing here, right? So if you include this, which is removing the NaN values, so this also we can include inside the pre-processing. So we have finished the pre-processing here, and so this is our final data set. Where we are going to do our the regression analysis. That is, we are going to fit the decision tree here. So this is xy. As I said, we are keeping the xy, the log of the C stock, and the independent variables. And this is the dependent variable. So now again, we are going to. So I think I have forgotten here. Oh, so here itself I have set the seed. Maybe I can push it down so that it is similar to the previous work that we had done. So we are setting the random seed and getting the training data. And here we are fitting our decision tree. So again, this is our dependent variable, and this after this similar sign, whatever the variables are, they are our independent variables, and they are available in a data that is denoted by DSM underscore data. Now we have some controls for that. We have specified our part dot control as min split is equal to 50. So what does that mean? So when we are making the decision tree, we'll see the decision tree here. But when we are making the decision tree, what we'll see when we are making the decision tree, what we'll see is that the decision tree. Let me run this, and maybe then it will be easier to explain. So if you see this decision tree here, so you see that there the nodes are splitting at some point. So this control, that is mean split is equal to 50, is telling us that to make this kind of node or to split this into two different divisions, you should have at least 50 points at this node. Now, what what would we expect when we have set this min split to a lesser value? We should expect more number of divisions. So let's try that, and let's see if we are getting. So I am saying that minimum number of points at a node need not be 50. They can be only 10, and then I will expect my node to split into two branches. So let's see if we are getting that. We don't need to run the whole thing, we can just run this thing. And as expected, we are getting more number of branches if we set the minimum split criteria to a lesser value. So if you see, you can compare these two, and we are getting that. And so you can play around with that. So this can be helpful. So the I have only sir has only showed only one of the control criteria. You can go ahead and check in the internet. There will be a lot more control criteria, and you can play with them, and can increase the goodness of it of your this model. So we have trained our model and saved it in the edge.rt.ext. Now we'll do the calibration. So we have fitted our model. Let's see what is the accuracy of our model in the calibration data. So first we do the prediction using and store it in rt.pred.c. That is .c meaning we denote it, that is the calibration data, and we use the goof function, that is the goodness of fit function. So we check the observed values and the predicted values, and then predict what is on the, then calculate what is the R square and what is the concordance, mean square error, and RMSE. So if you see here, you have R square value of 0.52, which is not very good. So let's see, if we had 50, then what kind of R square value we would have gotten. So for the calibration data. So if we have 50 min split, that is the minimum number of points to be 50 for allowing the decision tree to make a new branch, you see the R square value has reduced. So that's what I was saying, that you can play with these values and increase your R square value. Now let's go back to our 10, which was giving a little better. Or let's see what do we get the goodness of fit in the validation data set. So what can happen is, you if you have set the min split as a very low value, there can be an overfitting. So currently our min split is at 50, as you can see here, the last run command. So now let's check, and our R square value for the calibration data is 0.341. Let's check the R square value for the validation data. That is 0.289, close to what we are getting in the calibration data. Let's see what will happen if if we had used the min split of 10. If it is giving good values for the validation data, then we can use that also. So just to maintain the clarity, we'll do the R square value for the calibration data also. So calibration data R square is 0.50, and let's see the R square value for validation data. It is 0.499. So decreasing the min split has actually shown to be beneficial for us and increase the goodness of fit of our model. So you can also try to do that and play with that value. Now, as we did uh, in the last method, that is the multilinear regression, we predicted the values at the grid, and then we projected it onto a map. So this is also doing the same thing. So we just run this line and visualize the predicted log of the carbon concentration between 0 to 5 centimeter depth. So that's all for the decision tree. Now let's go to the part 4, where we have cubist, random forest, and universal kriging. Okay, so we start with the pre-processing of the data. So I'm just going to run this thing again. First, I will clean this, all the stored data, all the stored plots, and I'm going to run this model and pre-processing of the data again, because this is similar in all the regression methods. Now we fit the cubist method. So before we do that, let me talk about what is this cubist algorithm is doing. So cubist is fitting not only the linear regression. So if you go here, it is actually, you can say it is a combination of the decision tree and the linear regression, because what mainly happens in the cubist algorithm is to show that maybe I need to run this particular algorithm or decision tree, and I will try to explain that. So yeah, see what happens in cubist is, you have divided your input data into branches. Now you will fit linear regression for each of the data, each of the divisions separately. So let's say, so I am not saying that this is your qubit tree, but let's say this is your one batch of your input data. So when your RADK value is between this range to this range, you all the input values are falling into this particular batch. So there will be a separate linear regression with separate coefficients for all the independent variables that are going to give you your log C stock 0 underscore 5. And let's say this is another batch, then there is going to be a separate linear regression coefficient and equation that will be fit here, which is going to give you your dependent variable. So that is what is done in the qubit algorithm. So I'll just delete the plot. So now let's load the library and split the data into training and store it into MDAT. And here is the fitting that is going on. So we have X, that is our independent variable, stored into a data frame. And then we have our dependent variable, that is MDAT. In this data frame, the dependent variable is log C stock 0 underscore 5. And we have specified some qubit control parameters. So what are these control parameters? So let's look them one by one. So there, so we when we say rules is equal to 10, then we are specifying, or we are telling the qubits that you can use maximum 10 rules to divide your input data into different regions. So not necessarily, as sir mentioned, not necessarily the qubit algorithm is going to divide our data into 10 different domains, or not necessarily it is going to use 10 rules. It is going to do some kind of iteration and going to select an optimal number of rules. But we are telling it that you cannot go beyond 10 rules. Otherwise, what we can have is a separate equation for each of the data points, that will be a gross overfitting of the results. And then extrapolation is equal to 1. So extrapolation, when it is 0, then it says that if at all you get a argument or the independent variable that is outside the range of these values that are already given, then you don't perform any kind of extrapolation. And when you say extrapolation is equal to 1, 2, 3, 4, and you go higher and higher, you are telling it that you can perform extrapolation to a higher and higher degree. Then what is this committee? Committee is equal to 50. So in such thing, committee was set to, let's say, 5. What does this committee mean? So we kind of perform bootstrap and bagging uh, for this qubit. So when we have committee is equal to 5, then your qubit algorithm is going to train 5 different models based on the random sampling of your input and output variables. And then it is going to give you the output, final output, after averaging the values that are get obtained from the individual qubit model. So here I have reduced the model from 50 to 5. So if we run it, we will see that if you do the summary, we have already ran this. If you So we have ran this for 50. Let me run it again for 5. If you do the summary of it, you will see that you have 5 models, right? So you can go here and you can see that we have, when we set committee is equal to 5, we are we are making 5 models. And you can see also the rules that these models have used to divide their data set. Now just to stronghold this point, I'm going to increase this committee to, let's say, 10, and we'll see whether we are getting 10 models or not. And we have fitted our model. And now let's see the summary of the models. If you see, we have 10 models, and now we have exhausted all the 10 rules, right? You see, we have models and rules specified nicely in the summary. Now we can do our calibration and validation. For calibration, we use predict, and this is our model. We have trained our model and given this, stored it in this variable. Then we give the new data, that is the calibration data. And then we store the value in this variable, and we can use again the goodness of fit function with the observed data for the training set, and the predicted data just we predicted above here, and get the goodness of fit. So you see our R square value is very low. Now let me try to increase our model, and try to increase our rules from 10 to 50. So this is a gross, I know, very heavy increase at once. So this can kind of give you some kind of overfitting. But let's see what is the R square value for our calibration data now. So we have 50 rules and 50 models. So if you want to see, then you can again see that you'll see the models are starting ending at 50. So you have 50 models here. Now let's see what is the R square value for calibration. We have 2.255. So if you remember previously, I'll have to scroll back a lot, so I'll not do that. Previously, when we did only 10 committees and 10 rules, our R square was not too much different from this. So we don't need to make our model more and more complex. So we'll just keep the committee as 10, and you know uh, our rules as 10, and we are going to set up the model again and get the value of R square for calibration. So you have 0.263. So this the less number of rules and committee are for some reason performing better than when we had more rules and more models that we were training. Just a minute, I just a second. I think I by accident stopped my sharing of the screen. Oh, okay, 1 minute. Okay, so probably, yeah, just 1 minute. And okay, yeah. So I should be able to share my screen again. Oh, I'm still not able to share my screen. Share the screen. Okay, fine. We'll do it here. Let me just give me a second. Screen one, that is this, and screen two is this. So let me know if you are able to see the screen. Oh, okay, yeah. So I have checked that I'm able to okay. I'm able to share my screen. Okay, good. Let me check the recording also if it has not stopped. Yeah. Okay. So, what was saying last, yeah. So, increasing the number of rules, that is going to divide our input data into different branches, and increasing the number of sub models that will be used in the bagging, the bootstrapping and bagging didn't help much. So, we are going to keep the rules as at 10, and committees also at 10. Yeah, and now let's get the goodness of fit for our validation data set. So the R square for our calibration data and the validation data is not that much different, even though it is less. So that you can play around with your cubist control, and or we can perform some kind of data transformation apart from the log that we are taking, and we can potentially increase the R square value and get a better model. So that was for the cubist. Now we can use this script. I'm not going to explain it again, to just plot this prediction results onto a map. So we'll just run this script, and we'll see a map will show up just on this right side. So you can see the cubist model predicted a log of the carbon stock in the soil depth from 0 to 5 centimeters. Okay. Now let's go to the. So we have two more regression algorithms, that is random forest and universal kriging. So uh, we'll load the package random forest. So what does this random forest do? Random forest also is, just a minute. Maybe we can run this algorithm, and using the result I can explain that what is going on here. Just a minute. Okay, so needed to run something in the my command prompt. So first we'll perform the seeding, and we'll split our main data into training data, that is 70% of our data, and then we'll fit our model. J- Okay, I am seeing some error in my uh, comma in my Google Meet. Please let me know if you are able to hear my voice. You can type it into a chat. I'm able to see, but I'm not able to. Okay, so no response here. Okay, I assume that you are able to listen to me. Okay, yeah. So what we have done here is we have fit a random forest with a dependent variable as log of c stock underscore 0 underscore 5, and our independent variables as all these five covariates, and they are stored in the DSM. And we have given the importance is equal to true. So this argument computes and stores the importance of each predictor variable in the random forest. And this, when we say n trees is equal to 1000, then we are saying that the number of trees that we are getting, that will be you know number of trees that we are going to use. That is this is actually similar to the bootstrapping and bagging in the cubist. So that will be 1000, and then we can kind of do the averaging of these things and get the result. So you can see here that after doing this, we can see our importance plot. So as sir showed that then elevation is most important than TWI. So because the set dot seed 123 in my case, because my R version might be different from sir's R version. So the set dot seed, which is used basically for making this sample data, it is not the same. So my for me, in my case, this importance, the which variable is which variate is more important, might be a little different. So you don't worry that in your case, if it is different, that you don't think that it is wrong. So this plot is just showing that which variable is most important. So we have elevation, then TWI, RADK, Landsat B4 and B3 when you talk about purity. Okay, then we have fit our model and stored it in edge.rf.exp. Now let's calculate the R square for our calibration data. So first we'll predict the value using the random forest for our calibration data and store it in this variable. And then using the function goodness of fit, we will uh, compare the observed value and the predicted value and get the R square. Oh, so sorry, I selected it and then I have to select the whole thing or nothing. So we can see that we have a nice R square of 0.8837. Let's see if it is because of overfitting, or it is the model is actually nice. So an R square value of 0.83 and for validation and 88 for calibration, it's not that far. So we can say that our model has actually fitted nicely. Now let's try to reduce this entry to 500 and oh, I stopped. I was typing in a different screen. So now and let's run this. So now we have number of trees as 500 in this forest instead of 1000. So let's see what do we have for our calibration. So if you see carefully that R square value is not changed a lot when it comes to when we reduce the number of trees for the calibration data. But let's see if it is not decreased a lot in case of validation data also, then the number of trees need not to be that much high, and because it is just going to increase the complexity of our model. So let's check the validation data set. So if you see, we have 0.839 compared to 0.830, a slightly higher R square value, but we should not make that conclusion as of now. But with the conclusion or the inference we can make now is that we didn't need 1,000 trees to train our model. We didn't need 1,000 individual trees trained on randomly sampled bootstrap data, and then to get an average which is close enough to the actual value. We could do it with 500 itself. Let's for fun, let's just say if we do it for 100, what happens? So we have run it for 100 model. So we have 0.86, slightly lesser than the previous R square for the calibration data. But what about our validation? Our validation data has increased 0.84. So what does this tell us? So as also sir expressed this concern briefly in the session. I think I should highlight it. When you have more number of trees, this many high number of trees, you are prone to overfitting, and I think we can agree that that is what was going on in this particular when we set the entries as 1,000. So when we have 100, we have a more general model, and that's why it is able to predict nicely to the unseen data, that is the validation data, and give a higher value of the R square. Right now, again, using the function that we have used earlier, we can plot this data into a map using this function. So I'm not going to repeat what is going on here. We are just using the stacked covariates and the function to get the value of at these x and y and plot it here. Okay, so that's for random forest. Now let's go for universal kriging. So before universal kriging, last time I was not able to explain. Someone asked me about kriging. How does this kriging work? So let me just take this time and try to explain a little bit as best as I can, not going into much of the mathematics, that what this kriging actually is, how we get the parameters. Maybe it will give you a little bit more confidence. So I'm sharing another screen right now. So my yeah, just a second. I think I need to do this here so that I am recording nicely. Okay, yeah. So let me open my notepad. Yeah. So you are able to see my notepad, right? Okay, yeah, I can see that it is visible. So we'll start with this concept of this kriging. So basically, let me just briefly recall that when we had different points and we want to know the concentration at this point, this concentration is unknown, then this is a classical problem related to spatial interpolation, and we could use the deterministic interpolation, which were one of the examples were inverse distance, which is going to use the inverse of the distance as the weightage, you know or we can do some stochastic interpolation. That one of the example was kriging, and we discussed ordinary kriging. So what this inverse distance interpolant failed to account for was the spread of the data. So if you have a lot of data at this point, then unfortunately what you are doing is giving this particular region where the soil might have some kind of different property. Unfortunately, you are giving this particular region more weightage, even though each of the individual weightage may be small, but the region as a whole will have higher weightage compared to these other regions. So your value can be biased. So this is, this kind of thing is avoided in kriging, because it also it also sees the inter distance, sorry, the distance between the points, the spacing of the points, and then based on that it decides the weightage. So let's discuss it in a little detail. So this is what basically the equation look like. So we have our standard weights multiplied by the known values, and then we had the stochastic error, the residue we can say. So we'll ignore this for now. Let's ignore that for now. So you have lambda I, that is your weights. Oh, just a minute. Lambda I, that is your weights, and you have xi, that is the points where you already know the value of z. Like any other algorithm, we here also want to minimize the difference between the predicted and the observed value, right? So we are going to use a similar equation, and we are going to say that we want to minimize the expected value of the difference between the predicted and the observed value at that point. But if you look carefully, I kept uh, the Kriging in the Kriging equation, I kept my output as z at x naught, right? So why am I doing y naught? So the thing is, here is the, and you keep this also in mind, that we want to keep the mean zero. So first, what we assume in ordinary Kriging is that the mean is not varying specially. The mean of the value that we want to predict is not varying specially when it comes to the observation data. So what we do is we subtract the mean from the predicted data, and we get a new variable. So this is just for the variable namesake, and that's how we get the y. So we have to minimize this function. And now there is some lot of maths that I'm not going to show here, but just I'm going to say that whenever we are going to minimize a function, basically, if you have done your normal numerical techniques, you know that we have to subtract, sorry, do some kind of derivative, find the stationary points, find the global or local minima, and then based on that we find the minimum point. So same thing we are going to do here. For that, a video I found, I scoured the internet. It was not easy to find, but there is a video which kind of explains this derivation process. I will share the link of that video. You can go through that. The final end product of the equation is, if you want to minimize this particular difference between your predicted and expected value, you need to satisfy this equation, where these things, that is the variance, are known to us, and these are the weights to identify which we are doing all of this variogram process, right? So if you remember, I said that we will use the variogram, right, to get these weights. So here is where the variogram comes. So variograms is basically a function of the distance between points, d or h you can say, and then the semi variance, right? So you use this variogram, fit a function to it. That is, sir showed that you can fit an exponential function, fit a spherical function. You fit a function to it, and then using that function, the y value, the output of that function is going to be your these variances. So you fit an equation to your variogram, get these variances, and you just basically then you can do the inverse of this matrix on the right side and you can get the value of your weights. But let's look at these things. What are these variances actually? So sigma 11 is the variance of the point of the first point of your known data with itself. Sigma 12 is of the first point with the second point. Sigma 13 is the first with 3. So when we have a 3 by 3 matrix, we will get a 3 by 3 matrix when we have 3 observation points using which we are going to perform our interpolation. So if you look at this map, the rough map that I drew here, so if you have some layout which resembles something like this, so this is your x0, x1, x2, x3. So you have 3 points where you know the values and you want to predict x at x0. So your sigma 11 will be the covariance of this value with this itself. Sigma 33 will be this thing. Sigma 22 will be this thing. Sigma 12 will be here. Sigma 13, sigma 23. Right? So this is how you, and these values you will get from your variogram. But what about the sigma 10? So if you look at it carefully, I have given this unknown point as x0. So sigma 10 is nothing but your covariance of this x1 with x0. And this is your 30 and this is your 20. So when you have fit the model, you will get some equations. Using that equations, you can get the value of your sigmas. And once you know the sigmas, you are able to get the parameters. Now, so this is what basically I should have been able to tell last time, but I was not familiar with this kind of process. So I'm just going to tell in this video. Now here is the difference also. So if you just before after this, if you remember, we are going to discuss something called universal, sorry, I always put 2G in there, universal kriging, and previously we discussed ordinary kriging. So what is the difference between universal and ordinary kriging? So this is where this mean plays an important role. So we'll not look at the mathematics of universal kriging because that is that is too much out of the scope, but I will tell you that how is it different from ordinary kriging. Ordinary kriging assumes that the mean of the observation that you have is not spatially varying, whereas your universal kriging takes into account this factor also. So ordinary your observation, let's just say that since we are going to do the log of the carbon content from 0 to 5 centimeter, so it may, the mean value, the temporal mean of this log of carbon concentration is not going to be same at all the spatial points, right? That is what is the assumption of our ordinary kriging. Whereas our universal kriging, it uses one of the variables. So what we are using from from past some time, we are using elevation, we are using TWI, we are using RADK, Landsat B3 and B4. We are using these independent variables to make this prediction, right? So universal kriging is going to take one of these independent variables and try to fit and try to see the variation of the mean of this observation data with one of these variables, and it is going to try to have the this mean that we assume constant also spatially varying. So it is going to capture more more trend than the ordinary kriging, and that is how it is going to be more accurate than the ordinary kriging. So that is just a roughly I want to explain that difference between the ordinary kriging and universal kriging. In one line, if it is asked, then you can say the mean of the observation data is assumed constant in case of ordinary kriging, and it is assumed specially varying in case of universal kriging. Now let's go to our code. Okay. So, yeah. So now let's do our universal kriging. The method is not much different from that we have seen in the ordinary kriging. Just one thing to note that sir also mentioned is that our coordinate reference system for this both the covariates and the edge-Royce flying carbon needs to be in the same kind of same format. So this is again we are loading the package. So for this we need a gstat package for raster rgdel. Then we are fixing our randomness so that we don't get different value whenever we run. Uh, we don't get different training set whenever we run our model. Otherwise, we will not be able to know whether the data has changed or the variables that we have changed is giving a more r square value. So we okay, let me do the seeding again and then training, and then we are storing our training data in a data frame called cdat. So you can go here and see cdat, and then basically we are telling the r that x and y are nothing but spatial coordinates. So if you click on it, you see previously it was nice data frame kind of format. Now it has converted to spatial point data frame. And then we are here what we are doing is we are setting up the coordinate system for the cdat and the curves type from which we are going to extract the data in the same to the same value. So you can just run that. Now we are going to fit our variogram. So this is a variogram which knows that this is log c stock and 0 underscore 5 is your dependent variable, and these 5 are your independent variable, and they can be accessed from a data that is c data, and width is 250, Cressy is true, and cutoff is 1000. So let me try to explain the significance of these. Just a minute. Yeah, the significance of these inputs, width and cutoff, they both are used to identify which of these known points inside this elevation twi red k and all these things are going to be used to fit the variogram. So when you say width, so the points that are within 250, whatever the unit of distance is inside these things, the points that are within this 250 are going to be used for this kind of uh, you know variogram fitting. And cutoff is saying that after the length or the range of 10,000, you don't worry about taking these points to fit your variogram. And when you say Cressy is equal to true, you are specifying a method. That is, just let me check. I'm forgetting the name of the method. Um, you are specifying. Ah, yes. So Cressy is equal to true. So you are specifying that you use Cressy-Hawkins is estimator to fit the model in your variogram. So we will just run that, and we'll again so this is parameterizing our variogram, and here we are going to fit our variogram to an exponential function, and we are going to store that to our model underscore 1 or L. So we have nugget 0, and range 0. So for some reason our range is 0. So let me try to use spherical instead of exponential. Let's see if that gives any. Yeah, so we don't have this warning, and we have our range for spherical equal to 388. Oh, so we had range for range value for exponential also. Well, that's fine, we can use spherical. So I have, in previous session I have specified that we can use different kind of functions to fit our model. So now, using this variogram that we have fit and we have stored in the model 1, we will perform the Kriging interpolation. So let's do that. So we have fit our Kriging model, and we have stored them in G the U underscore GUK. So let me see. And then we have our validation data set. But where are we seeing the go? Okay, so we have here. Okay, yeah. So let's come to that. So we have our this is our validation data, but for some reason we are not looking at the goodness of fit for our calibration data. That's fine. That's fine. So let's look at the goodness of fit for our validation data itself. So we accept all the training data. We are going to store all the data in the data frame, DSM data frame, into the VDAT, and then we are going to specify that x and y are the coordinate system. Then again we have to make this uh, the coordinate system for both the co-stack and the VDAT same. So we do that here, and in the end we are checking what is the coordinate system here. That is nothing to worry about. And this is where we are storing the validation data. So as I explained, what are all these values? So we have trained our model, fit our model. Now we are using it to predict in the validation data to see how much our model is better. Okay, so then we are going to check the goodness of fit. So R square value is very low, 0.141. So is there anything we can do to kind of increase this fit, this R square value? What we can do is we can potentially, let's say, if we want to, we can increase our nugget, we can increase our range, we can use, instead of spherical that previously we had exponential, we can use that model to fit. So now let's see if we are getting any good results for R square. Okay, so for some reason, oh, I have to make this right. I have to make the coordinate system same. So you see, that's why it gave me the error. Now let's run this again. Yeah, so we have R square of 0.138. So it's not improved, but you can play around with the value with different functions also, different kind of transformation of data, different width and cutoff to decide which points are being used to fit. And Cressy true is you can keep that because it is the best, very widely accepted method of fitting the model for the variogram, fitting the parameter for the variogram. And here we are just plotting. So what do we get from this Kriging method? We get the regression trend and the residue, and you can go and see we have stored the prediction results in this uk.preds.v. If you go and see, we have some predictions and the variance, or you can say the residues at these each points. So basically what we are doing in the last few lines is we are plotting them in a column fashion, where one row, two column is there, and we are plotting in the first column, we are plotting the regression value, and in the second column we are plotting the, let me see, what are we plotting here? We are plotting the variance. Yes, so let's plot them, and you will see that the variance of the residue will not show much variation. So it's taking some time. Okay, so because we are using the interpolation method to get the values at the these grid points, it is taking some time. So if you see, the variance is not showing much variation, and this Kriging predictions, the normal regression predictions are showing nice trends. Since the R square value is not very good, it's like hardly any kind of correlation. You will see that the previously the random forest, which was showing 0.88, which had a value of the log C stock from 0 to 5 as varying from 0 to 3.5. This particular, on the contrary, this model is giving from 0 to 6. But you can see that this model is not performing very well. So these values are not probably acceptable. So that's all for the universal kriging. Now we'll come to the regression kriging. So what is this regression kriging? Regression kriging is basically you fit, as discussed in the slides, you fit the regression model for your to capture your general trend, and you fit the kriging model for the uh, residue that is left after you have captured the general trend. So basically this is all again the pre-processing of the data, and splitting the data into training and validation part. So I'm just going to run this. The main part starts. Okay, so before that, let me remove all the values so that it doesn't create some kind of problem for me. So let me run this again. So now I have my training data stored into a table format, that is MDAT. Right. What I can do again, as we have done in previous session, is I can delete all the non-required values. But let's just use specify the columns which are our independent variables. So we have kept our training data into MDAT. Now we fit the cubist, that is so as I said, we are going to fit the regression for our the capturing the general trend. So we have used here cubist. You can use any of the other previous regression techniques that we have discussed. That is, you can use multilinear multivariable linear regression. So for now we are using cubist here, where these are the independent variables and this is the dependent variable. Then again, as I said, we have some control variables. So we want an unbiased prediction, so it will try to keep the mean as 0. And we have rule is equal to 100. So if you remember in the cubist, when I was saying, then I told cubist is basically trying to divide your input region, input parameters or input variables into different regions, and it is fitting linear regression in each of those input regions separately. So in that case, it is able to capture more complex relations apart from simple multilinear regression. So when I say rules is equal to 100, that means that maximum number of rules that I am allowing cubist model to use is 100. So it can use 100 rules to divide my input variable region. When I say extrapolation is equal to 5, so again, as I said, extrapolation is equal to 0, means if it is getting a new data which is outside the domain range of the training data that we have given, it is not going to do any kind of extrapolation if we have extrapolation is equal to 0. But as we keep on increasing the extrapolation here, the value 0, 1, 2, 3, 5, 10, like that, then more and more degree we are giving it more freedom to do the extrapolation, right? Then committee, these are all I'm not aware of these sample, zero and label. But what committee is equal to 1. Basically this is to check bootstrapping and bagging. So what we can do, in cubist algorithm, in cubist function, is we can either have one model trained for all the data, or we can have various models trained on the sample data random sample data collected from the available data. So when we say committee is equal to 1, we are only having one model. When we say committee is equal to 5, we are going to train 5 models, that and the result final output that we are going to get is going to be the average of the 5 models. So standard a kind of bootstrapping and bagging kind of technique. So let me use 5, because always some kind of average is better. So let's fit the model. So we have fit our model. Now let's get the residue. So since we want to uh, use kriging for the residue, we will get the residue after we subtract the actual value from the predicted value of the linear regression that we have used. So this is to predict. We have trained our model and stored it in this variable that we are using, and we are giving it the new data is nothing but our whole training data, and it is going to give the residue of our whole training data, and it is going to add to our MDAT. So let's do that, and let's see. Let's take a look at our MDAT. So if you take a look at the MDAT, in the end you will see we have added the residue. So this is going to be used for our kriging. And we can also see the mean of our residue. So you see that mean is pretty low. Yeah. Now, if you remember, we said that doing the kriging, we need to kind of keep our CRS, the coordinate reference system, into the in same as our curve stack, that is the elevation, the other rasters. So we are doing that here. So we can see our MDAT is changed to the spatial coordinate or the spatial point data frame. Then we are fitting the variogram. I have already explained these variables. Then this is our variogram fitted here with spherical function, range 5000, and nugget 0. So nugget we have 0, range we have only 384. So it's like the maximum range we have specified here. Now we have fit our variogram, and using our this variogram, we can get the value of the residue. So if you see here, while fitting the variogram, we have given the residue as our dependent variable, and again here also our dependent variable is residue. So this just to solidify that we are fitting the residue using the kriging method only for the residue, and this is to get the grid. And here is where we are performing the prediction for the validation data, and we store it in cubist for our cubist algorithm. This is for our cubist algorithm, and same thing we are going to do for our kriging algorithm also. So again, we are separating the validation data from the training data set. We are telling the R that it is in spatial data format, and we are making the coordinate reference system same. So that is all being done here, and then we are predicting the residue using the kriging method. But then again, when you are doing this prediction, your prediction is going to be in the this kind of spatial kind of data frame. So we are using this as data dot frame to convert it into normal data frame, so that we can use it later on. Okay, so now it is taking, oh, it has done already. That is nice. So now the final value is going to be, so let's take a look at this rk.pets.p. So as previously we have seen that this kriging method is going to give us the value and the variance, right? So since the residue value is already very small, here we can see the variance itself is higher than the value, but it is not of our interest. Our interest, the value we are interested is in this uh, the prediction value. So we are going to use that. So that is this. that is specified by this comma 3, that you use all the rows for the third column, and third column is the predicted value, and we are going to sum it up with our linear regression value that we got from the cubist kind of curve fitting, and we are going to store it in the final variable, that is rk.spread.find. And now we can check. So what we are doing here is we are checking the goodness of fit if we had only fit our linear regression. So we have r square value of 0.13. Let's see if we get any better value when we are fitting the uh, when we are using the Kriging method to fit the residues also. So if you see here, we have not obtained much benefit when we can even say that for all the troubles we have went through, we have not obtained much higher r square value, and this fitting is not, uh, this model that we have trained here, it's not very good in getting the value of C log stat and for the input variables, that is the elevation, TVI, Radke, and all. So then again, you can, as I said earlier, you can play with the value. You can increase your committees, that is the number of smaller models, smaller cubist linear models. You can increase them and kind of get a better average. You can make the number of rules high. So you can, as of now, for now we have 100. Let's say in the previously also in the, I think, part 2 or part 4, part 2 or part 3, I discussed that when we decrease the number of rules, that is the decrease the kind of the division in our input data, we avoided some kind of overfitting. So let me just do that. So let's make it as 100 10, and let's do this kind of fitting again. I want to run the whole thing, and I want to see do we have any kind of improvement. Okay, so we have some problem here. So I think I might have to run it from the beginning. Let me run it from the beginning till this point. Select and run. Okay, so r is equal rules is equal to 100 also is not playing much import, is not giving much importance. Sorry, the increase in the r square value. But then you can play with these values and you can try to get higher r square. And here we can plot. So first we are plotting just the cubist model predicted log of the carbon stock. Then we are plotting the we are plotting this residual using the regression Kriging model, and then we are plotting here the final prediction. So first we are plotting the linear regression using the cubist model, then we are plotting the residual that we have modeled using the Kriging method, then we are finally plotting the final values. But here also you will see that our random forest, which gave the highest you know r square of 0.89, these values are not even compared to this. Our r square for random forest, as you know, it was 0.89. Yeah, but then again, it is not the fault of the model. It is probably we have to do some kind of data transformation and some kind of more hyperparameters we have to check here, and using that we can get higher r square values. So I will share this script with you, and you can do that on your own. Yeah. So in the starting, no one was answering. So my question, I wanted to ask this. You can message in chat or you can speak. Were you guys able to access the R script that was shared by Sir in the session that Sir showed? Because I am not able to find those R scripts. So if you don't understand that, basically the code that Sir is showing in the session, were you guys able to access those codes? And not also not the data file that he told he will put in the forum, right? The two-step dot zip. Yeah. So the same problem I am also facing. I have contacted the TAs. Initially, I contacted them. I should not. Okay, I should not say much, but I am just saying that I am not able to. I have also failed to obtain that uh, two-step dot zip for the combined model. So unfortunately, I won't be able to discuss that part. But we'll discuss everything till that. So we'll discuss our uh, categorical models that are that is the multinomial, then C5, and then the random forest, and that will be all for this last session. What I will try to do is I will try to contact them again and ask them to share the data file, and I will put that data file in my drive, so that I think my drive content are easily accessible to you guys, right? The script and the code that I am sharing. Uh, I hope it is accessible. Otherwise, I have also shared a lot of codes. If it is not accessible, then you might not have much understanding just by looking at the code. So yeah, yeah, Prachi, yeah, Prachi replied last time. So Prachi, are you able to in Drive? So yeah, there is a link, right? So are you familiar with that link that you that in the NPTEL portal? If you click on that link, it is going to show you the link of the YouTube videos. So I am going to upload these things in the YouTube video, and then also the code or the written content. So you are able to access that, right? Yes. Okay. Okay. Good. Okay. So I apologize to Prachi if she's watching the YouTube video because she left the meeting. Okay, so then I will ask them to share the two-step.zip file with me, and I will upload it in my drive, and you can access that because I'm not going to stop the access for you guys onto the drive. So once I get those files, I am going to share those files with you. For now, we'll just we have to deal with these only the content that we have. Okay, so multinomial logistic regression. So if you remember in the week 3 or week 4, we discussed that we when we want to do some kind of categorization using the or the classification using the logistic regression, we use a sigmoidal function that restricts the that restricts our output value from 0 to 1, and then we set up a threshold, and then we say if the value of the output is greater than that threshold, then we say that yes, it is belonging to this class, and then we do it for multiple classes. So this is somewhat the theory of it is somewhat similar to this. If you remember the equation that sir showed, that was ln of p by 1 minus p is equal to alpha x plus beta y plus c, and something like that. Basically, that p by 1 minus p, if you simplify that, the log of p upon 1 minus p, it is another representation of the sigmoidal function only, right? So basically, this approach we are going to use to perform a kind of multi-class classification. So let's load our data set. So we are going to use different data set here. Uh, so we are going to use HV Teron data and Hunter covariate. And we are going to tell R that inside this HV Teron data, our which is as of now in kind of a data frame format, it is actually a spatial data frame. So you should convert it into a spatial point data frame. So R has done that. Now, what does this extract do? I don't know if I have explained it clearly last time, so I am going to do it again. We are going to perform the interpolation, extrapolation onto this HV Terran data, but we need to know some of the some values at this HV Terran data. and we that values are stored in this hunter covariates data. We need to know the value of the covariates at these points, that is the xy points in the hv Terron data. So the extract function, basically what it does is it uses this grid type of data and identifies the covariates from these points, uh, from this data at these locations, using a simple method. When we say simple method, that is nothing but nearest neighbor interpolation or nearest neighbor kind of interpolation. So that is what is going on here. And now again our dsm is in spatial format, so we convert it into data format to get the value. So our let me just run it again, and I want to show you something. So our HV Terron, which had just X, Y, and Terron, at this X, Y, Terron is nothing but like the terrain number, you can say, just a category between 1 to 12. So the X, Y, and Terron. Now using this kind of extract, we obtained the value of AACN, drainage dot index, and all these variables at these XY locations of the HV Terron, because this X Hunter covariates is already having these value of the covariates at this location. We just wanted to extract them, and after extracting, we stored it into dsm.data, and we then converted that dsm.data from spatial format to data frame format. Now there may be some values that might be missing, and for that we are running this code to remove those values and keep only the values that are true. So let's run this. That is done. And now this is again splitting the data into training and validation. Now this is the multinomial function that is used. So this our target variable is Terron. We want to get the classes from 1 to 12, and these all are our independent variables, and we are using the training data. So we fit the model here, multinomial linear regression, and this is the summary of our model. So if you see, you will probably see the slope and intercept for each of the variables here. Yes, we are seeing that, and coefficients and standard errors. And then we can fit the model and get the probabilities of different classes, right? And we have the now we have the probabilities of different classes, right, for this particular training model. But I'm not interested in that. I'm interested in which class does the model belong to. So I can use this. So for our first this model, the class 1 has 30 points, class 2 has 1 point, class 3 has 86 points. So like that we can get another summary. Now what will happen in the future models that we are going to see, since this is linear model, it is finally it is able to predict, or it is able to assign some class to some values. But in future you will see that the C5 model and the regression model, they will say null or zero for some of the classes. That means they have not assigned any value for, let's say, class 2 will be 0. So in that case, all the training data is no training data has been assigned to this second class. So while plotting, we might have to remove one or two classes to get to plot without an error. Just to keep that in mind. Okay, now we have predicted the model. Now let's use the training data to get the uh, you know uh, goodness of fit for our categorical model for the training data. So we have a kappa. We have a kappa of 0.4499. So we have discussed the kappa again, and I have also shown you an example of calculating kappa from the confusion matrix, and we have also discussed in detail about the user accuracy and producer's accuracy. So I'm not going to go into that, but we can have these values of kappa. So kappa varies from 0 to 1, and the more it is closer to 1, the higher the, the better your model is, you can say. So this is our kappa for the calibration data set. Now we get the goodness of it for our validation data. So the kappa is not varying that much. So we have 0.45, we can say, and 0.39. So we can say the model is not overfitting that much. So there is not much you can do to increase the performance rather than doing some kind of transformation to your these data. So you can try that and try to see if you can increase the kappa of the model. This section is just going to plot. So we have the hunter covariate, which is basically the grid, and we have our model that we have trained, and it is class type prediction. So we specify the type of the predictions we have to do. Then we are going to save this into a file that is TIFF, which is having this format, and the data type is from integer to string, and overwrite true means basically that if this file name already exists, you just overwrite on top of that. So we just create our TIFF files for calibration data and validation data, and let's plot the calibration data onto the map. So here is where we are making the 12 different classes and assigning different color to it. So previous, I think SIR's R version is a little lower. That's why it was not showing the colors assigned to these um, hexagon coordinate or hexadecimal color system. Also, I am not using the same color system as SIR because I was not interested in copying, looking at the screen and copying all the color scripts. So I just created the just copied and pasted a color script that I found on the internet. So it may look a little different than SIR's expression. Oh, so we have to first make the level and then plot it. So if you see, this is our classification. So we have all the classes have some values. So that is why we are seeing some all the 12 variables here. So that is what for multinomial regression, multinomial logistic regression, which is not very complicated, as if I say so. Let's come to the C5 decision tree, which I feel is a little bit complicated, even more complicated than random forest. So let's start. This is basically, again, we are loading the data, telling R that it is. I will delete all the data first. We are loading the data, checking the value, checking the variates name, then telling R that my X and Y are nothing but coordinate system, and getting the extracting the value of the covariates for these particular X and Y location that are available in HV Teron, and then storing it in DSM data, and then converting it into a data frame. Then again removing all the missing datas, making selecting my training indices, and loading my C50 or C5 library. Here is where now we are fitting the model. So let's look at this. We are fitting the C5 model and storing it into variable hv.c5. This is having independent variables in a data frame, that is x. We are giving x equal to a data frame of the independent variables, and y is equal to of the our dependent variable. We have trials is equal to 5. So what does that mean? That means that the model is going to run through the data 5 times. If you recall me explaining the epochs in the deep learning, it is similar to that with slight differences. But to understand it, you can understand it like trials is the number of times algorithm will randomly split the data set to create different training and validation sets. Okay. And again, so some other control parameters. So CF is equal to 0.5 is nothing but the confidence interval or the confidence factor. If you remember, we say we use this in our normal distribution, that is the confidence interval. The same confidence interval is this. Min case is minimum points required to split the node, similar to the cubist, similar to the decision tree. And early stopping is if you have converged, then you can stop early. But we are saying that early stopping is false. So the default iterations, that is I think 200, it has to do all the iterations. So we have run our model. Now let's perform the prediction. So these are all our predictions. We can see here each value is being given one of the classes from 1 to 12. Now let's store this prediction and calculate the goodness of fit for our categorical model. So our kappa is 0.45. We can certainly try to change some of these hyperparameters and increase the goodness of fit. Then we have the goodness of fit for our validation data set, that is 0.35, slightly lower, but not so much lower that we have to say that our model was overfitted. So that's a good thing. Now, now here is where we are plotting. So again, to plot, we are going to use this Hunter covariate, which is having a raster data, a graded data, and we are going to use our model. And this is a class type prediction. So we have to give the type is equal to class. Then we'll store that, and these are all the formats that we have discussed. So I'll just go run it. So here is okay. So here is something that I forgot to show. So as I was saying, that multinomial logistic regression was simple algorithm, and we were able to kind of get each class had its own this at least one point was inside a class. But in C5 decision tree, what you will see that you the class 2 doesn't have any point in it. Class 9 doesn't have any point in it. Class 11 doesn't have any point in it. Now this can change if you change your covariates. Sorry, if you change your hyperparameters. But for now, to plot, we'll see out of the 12 classes, only in the output we'll know only 9 classes. So we have to give here, if you look at this carefully, I have given the labels only 9 and corresponding colors also only 9. So when I give you this code, and when you are changing some things before plotting, you just make sure that you are looking at this and you are able to see that you have the number of legends and the colors same as the number of values which are having some at least one point in that class. Okay, so let me run this and you'll see only 9 plots are coming without any kind of error. Okay, so that's that about C5 decision tree. Now our last topic for the day and for this session, random forest.r. So just again loading the data, transforming the data into coordinate system, then extracting the points, and then transforming the extracted points back into the data frame, then removing all the values which are missing, then splitting the data into training and calibration, and loading our random forest and fitting our random forest. And we can also print the random forest, so we can see that which variable is most important here. So in similar to Sir's lecture, we are also getting that the TWI is having the most importance out of all these independent variables. Now we can predict is for our calibration data, and we can see what is the goodness of it. So this we can even leave this because it is just going to show the values. Yeah, we can run this, there's no issues now, and we can store it in the calibration and get the goodness of fit for our data. So what do we see here? we see that kappa is equal to 1, and user's accuracy, producer accuracy is 100%. That means all the data, the calibration model is 100% accurate. Now whenever you see this 100%, now red flags should, the red light should start, lighting up in your brain that we have done some kind of mistake. So we'll come to it, we'll try to rectify this. But let's see, do we get this high kappa for the validation data set also. So when we perform the goodness of fit for our validation data, what do we see? We see that kappa is not even zero point 0.8 or zero point 0.6, it is 0.4. So that means definitely our model has overfitted, and that is mostly because of the number of trees that we are giving. So let's say if we give only trees as 10, let's say I give only 10 trees and I run this again. Let's see whether we get kappa of 100 or not. No, we are getting a kappa of 0.97, which may be fishy if our validation kappa is also not as high as this. Validation kappa is again 0.37. So we have come a little worse than before. So let's say if I give trees 2, make a more general kind of model, then let's see what is our kappa for validation. So we have kappa for calibration as zero point 0.7. Let's see the validation kappa is 0.26. So for some reason, actually I think we have missed the optimum number of number trees, which is going to give us the best validation kappa. So you can play with it. I'm just going to do the last one with 20. So you see with 20 it has increased. So there is somewhere between 20 and 100. You can play with it and get the value. Yeah, but here is the thing. Now you see the group 2, the class with 2, and the 12th class is not having any of the uh, it's not having any points inside that. So when I am plotting, so previously when I did this, when I wrote this code, I was using the entries as 500. So in that case, at least I was getting 1 point in each class. But now for this instance, I am not getting points for the second class and the 12th class. So if I just use this code, which is actually giving the 12 labels to plot the map, I am going to get some error. So first, let's just do the saving and making of the map and run this. So when I do this, okay, then you will see that will get some kind of an error. If it doesn't give an error, then I will be surprised. Okay, so that's interesting. So probably the error, the cause of the error is null rather than yeah. So let me correct myself. So when you have NaN in the class, then you need to reduce it. If you have 0, then it is fine, and that's what we got in the random forest. So sorry for that mix-up. So it's not 0. If you have NaN inside your NaN value, or not a number points inside your class classification, then you can use. Then you have to reduce these legends. But if you have 0, like in the random forest case, if you had 0, in that case you didn't don't need to reduce. And for some reason we are not even getting 0 now. So that's another thing that you can, that you can play around with and check which value is giving what. Okay, so that is, you can just delete all the plots, everything, and save the value. So that's all that we have for this session. uh, Unfortunately, we are not able to discuss the last combined model, because we need that data that was not available for me. And as I have asked Miss Prachi, Mrs. Prachi has told that she was also not able to access that data. So what I will do is I will ask the TAs personally, and if I will see if they are able to provide me that data set, and I will share it in my drive. So you can practice that and yourself and try to see what you are getting. Okay, so that's all for today's session. Do you have any questions? Then I can try to. Oh yeah, before I end this, I want to share something with you guys. I think you will probably already know all these things because it has been quite some time since that tool has come. But there is an amazing tool. So for me, as I told last session that I'm not very comfortable with R. I was not knowing what are all these syntaxes, what is the significance of these things. So I just and I probably may not be able to answer if you ask something related to this to me. But we have a very interesting tool that you can use, to identify this, and that is what I have been using. So that is, are you able to see my screen? So this is, I'm sure you would have heard of it if you are not living in solidarity of some kind. It is Chat GPT, which uh, which is an AI model. So this is the tool that I use to get the 12 independent color palettes. So you see, I asked it, give me 12 hex color palettes. It gave me in a list format. Then I asked it list them in a row within quotes. So you can give it commands like whatever you can think of, you can give the command, and then it listed them in a row within quotes and comma separated, right? Then still it was giving me these things, the name of the palette. So I told list them all in one row, and then I told them don't print the name of the palette before the color. So it gave me this. So I can just copy and paste. I just copy pasted the 12 first 12 color palettes into the R, and I was able to get away with that. Otherwise, I would have to search and type each of the things. And same way I we can search what is the C50 in R, and in the same way I search that if you look at that hunter, I explained to you what that extract does. So I got it from here only, that extract what is the function of the extract, what are all each of the variables, what are all each of the variables or the parameters doing, what are their significances. You can actually ask it. If you are not satisfied with the answer, you can tell it that I think you got something wrong, and it will automatically correct itself and give you the refreshed correct answer. So if you have some kind of syntax problem related doubt, you can ask this chat gpt. You may need to register your email id. So if you are comfortable with that, you can ask this, and it is completely free also. You don't have to go the chat gpt premium. So that's very interesting tool that I wanted to share with you. Okay, so that's all for today's session. You can ask if some questions are there. If you have some questions, you can ask them. I'll try my best to answer. Okay, so if there are no questions, thanks for attending the sessions, and thanks for all of you who are watching watching this recording. And I hope you all do well in your exam. All the best, and thanks.